Hello everyone, I'm Fengyu Liu from Fudan University. Today, I'll be sharing our research on security in microservice architecture. Our talk is titled Detecting Taint-Style Vulnerabilities in Microservice-Structured Web Applications. Before we dive into the technical details, let me briefly introduce our team. I'm Fengyu Liu, a PhD student at Fudan University, and a core member of the Wizard and Recapig CTF teams. Our team is currently ranked #1 in the CTF team in 2025. My co-speaker is Youkun Shi, a postdoctoral researcher at the Hong Kong Polytechnic University, and one of the co-founder of Wizard. Okay, here's a quick overview of today's agenda. We'll start with some background and industry context. Then we'll cover the attack services in microservice and look at a real-world case study. After that, I'll explain how our tool MScan works, followed by our evaluation results. Finally, we'll summarize our findings and share key insights for the attendees. Let's start by looking at how AMPs have changed in recent years. We used to build everything as one big unit called a monolith. Now, most app companies split their web apps into small, independent services, what we call microservices. Today, most scalable apps rely on microservices. Each service does one job, and teams can update and deploy them independently. This setup brings speed and flexibility, but it also means security issues can spread more easily. Let's walk through how a user request travels in microservice apps. At the center of microservice apps is a gateway. It directs all user requests to different internal services based on flexible routing rules. For example, the gateway might let users reach the pod service but block direct access to the user service in this picture. This helps manage traffic, but as we all see, these rules can sometimes hide security risks. Once requests enter through the gateway, they are passed from service to service inside the system. Microservices communicate using lightweight tools like REST APIs or gRPC. This setup gives teams a lot of flexibility, but it also means sensitive data travels across many services. So one weak link can spread security problems to the rest. Now that we have covered the basic structure of microservice systems, let's talk about where security threats can appear. I'll walk you through the main attack surfaces, including risks inside a single service and those that span across multiple services. First, let's look at intra-service vulnerabilities. This happens completely inside a single microservice. For example, imagine user input goes straight to sensitive functions like eval without any checks. These bugs are usually easier to spot, but they still pose real security risks. Second, the inter-service vulnerability and the trickiest to catch. Here, tainted data can travel across several different microservices before it reaches a sensitive operation, like eval. For example, user input may enter through a portal service, get passed along by Kafka to a user service, and only then be misused. Individually, each service might look secure, but together, they can expose hidden risks. To sum up, taint-style vulnerabilities in microservices can be either confined to a single service or spread across multiple services. Now, let's look at a real-world case to see how these threats manifest in practice. Let's look at a real-world vulnerability in Spring Cloud Data Flow, a popular platform for building and managing data pipelines under the Spring ecosystem. Let's follow the journey of user input as it travels through multiple services. In this case, user input first enters through a stream service in the Spring Cloud Data Flow. This data then travels to another service via a REST template calls without any citation. Finally, the tainted value reaches the sensitive sinks, files.write, which expose a vulnerability that isn't obvious when looking at just one service. This example perfectly illustrates why detecting cross-service data flows is essential for real security. Now that we have seen a real example, let's talk about why detecting these vulnerabilities is so hard. There are some big challenges that standard tools struggle with. Understanding these issues or challenges will help explain why we need new solutions like MScan. Let's look at the first challenge, identifying real entry points. In this diagram, the APIs shown on the left are accessible to users, since the gateways permit them. The APIs on the right do exist in the code, but they are blocked by the gateway, so outside users cannot access them. Because these gateway rules change often and can be complicated, it's hard for detection tools like CodeQL to know which APIs are real entry points. This means that if we simply treat every API as public, we will get a lot of false positives. But if we miss a real entry point, we risk missing actual attacks. So it is important for our detection approach to really understand the gateway's behavior, not just the code. The next challenge we face is tracking data as it moves between services. Microservices use different communication methods, such as REST template, gRPC, or message queues like Kafka. These interactions create complex data paths that traditional tools, which focus on single services, have trouble following. Because of this, tainted user input can split through service unnoticed, making it harder to catch hidden security risks. The last big problem comes from the long call chain in microservice apps. User input can pass through several layers and many different services before it finally reaches a sensitive operation. Traditional analysis methods often struggle with these steps because they either take too long or run out of memory. This means that deep and complex data flows might never get fully checked, so some risks are still hidden. To tackle these challenges, we built a new detection framework called MScan, designed just for microservices. MScan is centered on three main ideas. First, we use large language models to accurately identify which APIs users can actually reach. Second, we build a service dependency graph to follow how data moves across all services. Third, we use a distance-guided strategy to keep our analysis both precise and scalable, even as the systems get more complex. So let's move to the first stage, entry point identification. Here, we use a large language model to read the gateway configuration files and pick out the real user-facing routes while skipping any blocked endpoints. Next, we match these routes to the actual API methods in the code, so we only focus on what's truly reachable. This precise matching decreases both false positives and missed entry points right from the beginning. In these images, you can see how we use a few-shot approach to guide the LLM. We show it several examples of different gateway rules and the real entries each time. Through these step-by-step examples, the model quickly learns to pick out only the routes user can actually reach, even with tricky patterns. This process makes our entry point identification much more accurate than traditional methods. Next, let's talk about building the service dependency graph. Our first job here is to find all the APIs that services use to talk to each other. Services these days can use REST, gRPCs, message queues, WebSocket, and even custom solutions. With so many options, covering every type of communication can be quite a challenge. So we put some real thought into how to handle all different methods. Instead of typing ourselves to a single solution, we decided to use a plugin system. This way, whenever a new communication method comes up or an old one changes, we can just add and update the plugin, keeping our taint tracking accurate with minimal efforts. Now, the last thing we needed to do is, in this stage is to match up identifier nodes, like a topic name or URI, to link sending and receiving service together. We use this connection to bring all the cross-service flows into one unified service dependency graph. With everything joined up, we can finally track taint data as it moves through every services, not just inside one component. This overall view allows MScan to discover vulnerabilities that single service tools would miss. With our service dependence graph ready, we are set to start the final step. Now that we have this graph, how do we find bugs? We follow 4 simple steps. First, treat user-facing API, parameters, and Taint sources. Second, follow how Taint spread across services, across functions. Third, check if Taint reaches sensitive operations like evil or file writes. And fourth, see if the data was sanitized on the way. If not, we report it as vulnerability. However, there are still big challenges left. How to make the Taint analysis both precise and scalable, especially given the extremely long call chain in microservices. That's where our selective, context-sensitive analysis comes in. Let's quickly review what context sensitivity actually means in Taint analysis. Context sensitivity basically tracks how a method is called, not just which method is called. That means even if the same method is called in different places, different call sites, we treat each call separately based on its calling path. This gives much more precise results because we can tell which Taint really flows into a method in a dangerous way, depending on the exact call chain and call site. Context-sensitive analysis is important for detecting vulnerability accurately. However, using full context sensitivity in microservice is not practical. Call chains in these systems often becomes extremely long, sometimes covering many services and layers. If we try to track every possible path in detail, the analysis used too much memories and can become very slow or even fail to finish. For this reason, traditional context-sensitive analysis often cannot handle large-scale vulnerability applications. So how can we fix the scalability issues while keeping the precision? In MScan, we take a smarter, more dynamic approaches. We introduce a distance-guided strategy. This approach adjusts how deeply we analyze context, depending on how close data is to a vulnerable things within the service dependence graph. If data get closer to a sensitive operation, we increase context sensitivity to improve detection accurately. Further away from the sink, we relax the bound, which helps us save memories and speed up the analysis without losing much precision. By guiding context sensitivity in this way, we achieve a practical balance between detection accuracy and the resource usage, making our method suitable for large-scale microservice applications. We have just walked through MScan's core design, from entry point identification to the service dependence graph and our distance-guided strategy. You have also seen how these ideas help tackle microservice-specific security challenges. Now, let's see whether the approach actually works in practice. In the next part, I'll share how we implemented MScan, present our evaluation results, and show how our tool compared to existing solutions like CodeKL. This will give you a clear picture of MScan's real-world impact. MScan is built on Taint, a SOTA pointer analysis engine. We wrote about 7,000 lines of Java code and made MScan support detection of eight different vulnerability types, like SQL injection, SSIF, and code injection. This strong foundation gives us reliable and comprehensive detection across real-world microservice apps. With this setup in place, we were ready to test MScan on challenging large-scale applications. You can find the code at GitHub. To thoroughly test MScan, we built a diverse dataset for evaluation. We collected 25 popular open-source microservice apps from different domains, each with over 1,000 GitHub stars. On top of that, we also included 5 large-scale industry applications from Alibaba Group, which features real-world core service complexity. This broad dataset helps us make sure our results truly reflect the security challenges found in real production systems. Now, let's take a look at MScan's real-world result. In our experiments, MScan detected 59 previously unknown zero-day vulnerabilities across all of our test applications. We achieved a precision rate of about 72%, so most of the issues we reported were truly valid. This is clear improvement over traditional approaches, and it shows the practical value our method brings. To put these members in context, we compared MScan directly with CodeQL, which is a widely used static analysis tools. On the same applications, CodeQL only found 23 vulnerabilities and missed 36 issues that MScan was able to discover. Its precision was also much lower, and under 40%. A big part of this gap comes from MScan's ability to handle gateway rules, inter-service flows, and complex calling context. Looking deeper at CodeQL's results, we found that many false positives happened because the tools couldn't understand gateway's configuration. So it flagged endpoints that weren't even accessible to users. CodeQL also had quite a few false negatives, mainly because it cannot track data across services and sometimes run into timeouts in large applications. This analysis highlights how important it is to support real application features when detecting vulnerabilities. To better understand the importance of each technique in MScan, we conducted an ablation study. We tested different variants by disabling or replacing key MScan components, such as entry point identification, the service dependence graph, and our distance-guided strategy. This helps us see exactly how each part affects the quality and performance of MScan. Next, I'll show you the result and what happens when any core feature is missing. Now, let's take a closer look at the ablation study results for MScan. Whenever we disable a single feature, we either lost detection accuracy or faced major scalability issues. For example, without SDG modeling, MScan completely missed vulnerabilities that cross service boundaries. On the other hand, turning off our distance-guided strategy often causes the analysis to run out of memory. These results make it clear. All three major components are essential for practical and effective microservice security analysis. Now, let me share a concrete example of how MScan works in the real world. This case comes from the well-known IoT platform, Sideware, where we discovered an SQL injection vulnerability. In this scenario, user inputs first arrives at the device REST portal, moving across services via gRPC, and eventually reaches a database query in the device event service. Traditional tools struggle to catch this issue because the tainted data cross different services. But MScan detects it by modeling all the inter-service communication in detail. This clearly shows why capturing cross-service data flow is essential for modern security analysis. Another real case is time from Udao Cloud, which is a widely used cloud platform. Here, an exposed file upload endpoints in the file REST portal let unsafe data pass through OpenVIN to the file REST service. OpenVIN is also a communication method. And at the end of the call chain, the file util.writeBytes operates accepted the unfiltered data, creating a risk for arbitrary file writes across services. Because the taint flowed through several services, traditional detection tools such as CodeQL would likely miss it. MScan was able to catch this hidden vulnerability because it can track data flow end-to-end in a microservice system. Our final case comes from Mogu Blog, which is a well-known blogging platform. In this situation, a user provided URL entered through the WeChat REST portal and was passed to the picture REST service using OpenVIN. This input reached the URL constructor, think URL.init, entered through the WeChat REST template portal, and was passed to the picture REST service. This input reached the URL constructor without any proper checks, making the system vulnerable to SSIF attacks. MScan was able to automatically detect this serious issue with its advanced context-sensitive analysis. Together, these case studies highlight how effective our methods is in spotting real-world vulnerabilities across microservice applications. Now that we have gone through our approach, evaluation, and real-world cases, let's close by summarizing the key takeaways. We have explored the main security challenges in microservices and seen how MScan addresses them. Attendees will know the current state and key challenges of detecting Taint-Style vulnerabilities in microservice apps, understanding how MScan works and why it detects Taint-Style vulnerabilities in microservice apps efficiently and precisely, and learn how to optimize Taint-Style analysis when adapting it to a cross-service system. Thank you for listening, and if you want more details, feel free to read our paper or reach out through the email. Thank you.